Welcome to Unit 4. In Unit 4 we're going to take a look at units and prefixes and systems of measuring, that sort of thing. You should read sections 1.9 or section 1.9 in your textbook and look at Appendix 8.2. It's been a while since you've looked at the concept of scientific or exponential notation. Four primary topics we'll look at here. One is called the International System of Units, the SI system. We'll look at the current definitions of what the 7 base units are in that SI system. We'll review exponential notation, which you can find information on in Appendix 8.2. And we'll look at metric prefixes and their interconversions a little bit, kind of get started on that idea. And the metrics, the United States is the only country that uses, about the only country that uses the British system of units. So what you find is you find things like the meter and the kilogram down here. Those are metric-based units. Other things, fortunately, the unit of time is the second. The temperature scale is a little different. It's called the Kelvin. And we talk about amounts of substance in terms of what we call moles. And also talk about electric current as amperes. You've probably heard that term. And luminous intensity is candela, which you may not have heard much, although you might have heard it looking at projectors. They're only talking lumens, I guess, of projectors. If you look at the symbols, the abbreviations for those units are pretty simple. For meter, just an M. Kilograms, just kg. There's the second, the Kelvin, and the capital K. And thus, even though Kelvin's a temperature scale, there is no degree sign in front of the K. The mole is my favorite abbreviation. You take a 4-letter word, the mole, M-O-L-E, and abbreviate it by knocking off the E and keeping 3 letters in it. Since these are going to be our 7 basic units, there has to be a very good definition of what these 7 units are. And so we have, for 6 of the 7, we have very scientific types of definitions. If you look at the very top one here, you talk about the second, it's just the duration of 9 trillion, whatever that is, 192 billion, so on, periods of the radiation corresponding to the transition between the 2 hyperfine levels of the ground state of the cesium-133 atom. This is not something you're going to use in your everyday life. Atomic clocks are based on this. The very precise times that we get with those are based on this kind of a system. And actually our second in general is, but for the most part, if you have to be somewhere at 6 o'clock, you don't really care if you're there within 1/9 billionths of the radiation, that sort of thing, or the duration, 9 billion periods of that sort of degradation of cesium-133. If you have to be somewhere at 6 o'clock, we pretty much round that. 6 o'clock, 6 o'clock. The meter is a length of that's traveled by light in a vacuum during this particular period of a second. And so we have these kinds of definitions for the most part. If you want to see what the others look like, you can go to that link, the page down at the bottom where it says http://physics.nis. You'll kind of see a list of those things. The kilogram is the only one that's not defined physically, and that's because we haven't figured out a way of doing it well yet. The other thing is we have this prototype of the kilogram. You'll see inside of the glass chamber on the right-hand side that there's a metal weight inside of there. That is the kilogram. We don't have a fancy way of defining it. That is the kilogram. He's sitting on a pillow over in France. And we have replicates of it. The United States has a replicate and all. There are several of them around the world. Interesting thing about the kilogram is back in 2007, some concern was raised because it had been determined that the standard kilogram, the one in France, has been losing mass over time. Now, it's not the kind of mass that you and I would lose sleep over, but it's the kind of mass that science-type folks lose sleep over. It's losing about 50 millionths of a gram in 100 years. If you put it in sort of a more conceivable format, that's about the mass of a fingerprint, which isn't very massive at all. Let's take a quick run through exponential notation. Let's go back and view that, because we're going to find out in this course that we'll be dealing with some very, very large numbers sometimes and dealing with some very, very small numbers sometimes. When you look at the SI system, it really looks like it's a metric-based system, having that meter and having that kilogram inside of it. The metric system is a very nice system once you get used to it. That involves just moving decimal points around. You can do a lot of metric conversions without even having a calculator around. And so it's a very important, very helpful system to be able to work in. So what we're going to do is look a little bit at how we take and convert from one metric unit into another. Let's look at exponential notation first, though. And if you look in the upper left-hand corner, you'll see 10 equals 10 to the 1. That just means that the 10 is just 1/10 is all it amounts to. If I take 10 and multiply by 10 right below that, I get 100. that means that 10 times 10, or 10 squared, is equal to 100. If I look at the one below that, look at the 1,000. I take 10 times 10 times 10 is 1,000, and notice that's going to be 10 cubed. And so what you get a sense of is that if I think about the decimal point, that I'll be moving the decimal point. I'm just moving the decimal point to go from a big number to something where I have multiples. If you look on the right-hand side where we have the 0.1, that's really the same as 1 divided by 10. And so now instead of having a 10 to the 1 like we have on the left, we have a 10 to the minus 1. The minus indicating it's 1 over. And so 100th is 0.01, is 1 over 10 times 10 is 10 to the minus 2, because I have two 10s down at the bottom, and so on. And so you'll notice that on the left-hand side that I take and put an exponent in, if really what it's telling me is the number of decimal points, the exponent's telling me how many decimal points I have to the right of decimal places I have to the right of my number on the very left. So let's take a look at some examples of converting these. Top one, I have the number 63,410. If you imagine the decimal point being right after the 0, I can move it to the left from the 0 to between the 1 and 0, to between the 4 and 1, between the 3 and 4, between the 6 and 3. If I move it 4 places to the left, I get 6.3410 times 10, and I'm writing 4 because I want to recognize I've moved it 4 places. I could have stopped at 2. I could have moved it over 2 places to be between the 4 and the 1, and then I could have written 634.10 times 10 squared, same number. By convention, we usually move it far enough over to the left or to the right in the small numbers so that the first number is between 1 and 10. If you look below that, there's 145.6. If I move it over 2 places to make it between 1 and 10, I write it times 10 squared. And if I look at the 0.00389 kilograms, same concept, but now I'm moving it to the right, so that means I'm going to have it 3 places to the right, to between the 3 and the 8, and that should be a 9 at the end. 3.80 should be 3.89, and what I should see then is it's going to be moved 3 places to the right. I indicate it's a minus sign because I've actually ended up making that number bigger in the end, in the front end. Those are just examples of the conventions, of the conversions that you might see in the metric system. Metric prefixes, you don't have to memorize all these. Really the milli, the centi, the deci, and the kilo, those kind of middle ones should be the ones that you're most familiar with. Some of these you've heard about more and more as computer things come along. A terabyte, now they talk about terabyte hard drives. Used to be gigabyte hard drives are pretty big. We talk about megas, megabytes in there. So you can see a lot of these larger units in terms of the metric system. I'm sorry, in terms of computers. If you go all the way to the bottom and look at the nano is something you may have heard of because the nano is a very big area of technology these days. Nanotechnology you may have heard of. We're talking about very, very small types of situations. So if you look at metric conversions, I made a little table here to kind of give you an idea of what we're doing directionally as we go up and down this table. We'll have the large units at the top and the small units down at the bottom. So what it tells me, if I'm in a smaller unit, I want to go up to a larger unit, I'm going to take, and looking at the arrow, I'm going to move the decimal point to the left to make that conversion. The number of places comes from looking at the difference in exponents between, for example, a tera and a mega. The tera has a 10 to the 12th, and the mega has 10 to the 6th. 12 minus 6 is 6 decimal places. If I want to go from a mega to a tera, I would move 6 decimal places to the left. If I want to go from a tera to a mega, I'd move it 6 decimal places to the right. Let's look at some examples of this. Top one, 42,600 meters, and suppose I want to convert that to kilometers. Well, what I can think about is, as I look at this thing, this number really is, meters to kilometers. Sorry. Meters are the base unit. The base unit means I have no prefix on it. Kilometers are the ones right above that, so I'm going from the base unit to kilometers. The difference in exponents is 3 minus 0 is 3. So I'm going to move it 3 places, and since I'm going up, I'm going to move it to the left. And so my 42,600 becomes 42.6. Down below that, if I want to go from kilometers to centimeters, I find my kilometers up on the top of the table, 10 to the 3. I find my centimeters down lower, which is 10 to the minus 2. 3 minus a negative 2 is 5 decimal places. I have to move it. And since I'm going down the table, I have to move it to the right 5 decimal places. So I move it over to from where it is now to 0.459. I move it 5 decimal places. Where I've run out of digits, I put in zeros to hold that decimal place. So it becomes 45,900 centimeters. 350 milliliters to liters. Liters is a base unit. We'll see that in the next unit. And milliliters is just a milli. So if you look at those, there's a 3 decimal point move. And if I'm going from milli to liters, I'm going to be moving it to the left. And you'll see the resulting 0.350 liters. And the very bottom one, huge numbers. This is where you're not thinking so much about drawing it out. Very, very big numbers down here. If I want to go from deciseconds to centiseconds, deciseconds is 10 to the minus 1, centi is 10 to the minus 2. I'm moving down the table. The difference in decimal points is 1 unit. The difference between minus 2 and minus 1 is 1 unit, so I'm going to move 1 unit to the right, which means that my number is going to be getting bigger, and my 34 becomes a 35. At the end of Unit 4, you should review the self-assessment on Unit 4. This information will be covered on quiz number 1, as well as the midterm and the final.